Thanks,
Oh,
everybody.
sorry. That was by webinar proper. Sorry, I was just gonna start off and introduce you and everything.
Ah,
So
right. Yep,
yes,
please do. My bad.
but yes, not a problem. It's always good to have our presenters raring to go. So welcome back to week 3 of this Networking Certification Essentials short course with IT Masters and Chalster University. As usual, my name is Jack Stewart, and we are joined by wonderful Kit on the back end, making sure everything runs nice and smoothly on a technical level for us. Our wonderful mentor this week, as for the last few weeks and for next week as well, is Ian Robertson, with over 25 years of experience in the networking space, as well as one of our mentors in several subjects in the cloud space, and a holder of multiple degrees from ITM and CSU as well. So excellent testimony to the usefulness and comprehensiveness of these courses. We are broadcasting to you today from the lands of the Wurundjeri people of the Kulin Nation, and we pay our respects to their elders and ancestors and acknowledge their ongoing and unbroken sovereignty over these lands and waters. Before we begin as well, just as usual, a little bit of housekeeping. If you've got questions for Ian about the content of the course, please direct those to the Q&A section, which you should see down the bottom of your Zoom window. If you've got questions for the administrative side, so if that's about your student portal, about enrollment, about eligibility and things, feel free to direct those questions about the portal and things like that. If they're short ones, you can pop them in the webinar chat once you set your chat to everyone to connect with your fellow attendees. Thank you, Kit, for popping that in the chat currently. If you've got any issues with the audio or visual aspect of this course so far, it may be an issue on your end. It seems I'm able to see everything as well. If you'd like to chat with your fellow attendees as well, please pop that in the webinar chat. And if you have questions about the course content, hopefully we'll get through a number of them throughout the content tonight. But if we are not able to, that is something that you can then direct to the student forums, which along with the course materials and recordings of previous weeks, quizzes, surveys, etc., are available on the portal at learn.itmasters.edu.au, as well as if everyone can please fill out that survey, which you can find a link to in the chat as well as linked on the student portal. That is really, really helpful to us in getting feedback on what kind of course content and how you'd like these courses to run as well, to improve our, to help with our, practice of continuous improvement in what we do. So we should be here for a little while now. Thanks everybody for joining us from all around the world and all of your different time zones. And I will hand you over now to Ian Robertson. Thanks, Ian.
Thank you, Jack, and thank you, everybody, for your time tonight or this morning, as the time might be for you. I see there's about 320, 330 of you on here. Great to see you all. Thank you for your time. And I hope that I can provide you some valuable insights into routing. We're now moving it back up the stack to layer 3. And so we're going to spend most of tonight talking about routing. So with that, let's sort of start with a 101. What is routing? So routing is the process of sending packets. Now, packets obviously are the smallest IP logical unit from one network to another network. As it says there, the key term here is network. So if we're talking about networks, we're talking about anything, be it a virtual LAN or a net or a local area network in general, with one or more connected devices to it, that is separated from other networks by dint of being its own broadcast domain. So routers do this by building what are called routing tables in memory. That they basically, we'll talk a lot about routing tables tonight, but essentially a routing table consists of the destinations that a router is familiar with, the destination networks, and the subnet masks that represent that network. We'll talk about that construct as well. Its next hop, so the next router and the path that will get it to that destination. And then, because in many cases there can be more than one possible path to get from one network to another, particularly once we consider the size of, say, the internet, we have concepts like metrics and administrative distances, which allow us to determine which of these paths we should choose. Now, the routing table basically talks about two different protocols. So there's the routing protocols themselves, which are, we'll talk a lot about them tonight. They're essentially the mechanisms by which routers learn how to route, how to pass information from A to B. And then there's routed protocols, which are the IP or IPX type packets that we're actually caring about getting from A to B. So you'll hear me talking a lot about both routing protocols and, to a lesser degree, routed protocols tonight. We'll mostly be talking about IPv4 because that's what the exams focus on, with a lesser focus on IPv6. IPX we won't really talk about. Those of you who are familiar with IPX are probably also familiar with a product called Novell NetWare, which to my knowledge hasn't been in significant active use for at least 20 years, possibly more. But that said, it is a routed protocol as well. And everything that we talk about tonight applies to it in broadly the same ways. So how does a router figure out what it needs to do? So to get from A to B, a router needs to consider three things. It needs to consider the length of the network that it's connecting to. That's called prefix length, and we'll describe all these terms in detail later. The metric, in other words, the cost of of accessing that particular path via that particular mechanism, and the administrative distance, which is another mechanism that works in conjunction with metric to determine the best possible path from A to B. So let's talk about what is a prefix length. So you'll see on the screen an IP address, 10.1.5.2. So that's an IP address. The network component of that is, in this case, with a /24, 10.1.5. So essentially what this particular network shows is that we have a host 10.1.5.2 that belongs to a network 10.1.5.0 that in this case could have up to 252 other hosts assigned to it. Now, it's very, very possible to have both 10.1.5.0 and 10.0.0.0 in a routing table. That's perfectly reasonable behavior for a router to take. And since technically 10.1.5.2 is part of 10.0.0.0/8, how does it decide which way to go? Well, routers will always choose the most specific path that gets them to where they need to go, on the basis that if they have a more specific path, it's clearly closer to them. And obviously, particularly with IPv4, there is the concept of a network containing exactly one host. 10.1.5.2/32 is a valid routing address or routed address, and it doesn't get any more specific than that. If you're telling a router to get to this device on this IP address, it's not going to be able to pick another path to get there because you've given it the most specific path that it can possibly choose. Now, administrative distance and metric. Metrics allow for multiple paths within a routing protocol. Now, we'll talk about this in more detail, so don't panic too much just yet. But the long and the short of it is that a metric allows you to have 2 or 3 or 4 different paths, all known to a router, and essentially to prioritize those. The idea being that if one becomes unavailable, the second or the third or the fourth will take over. So it gives you a form of redundancy. Now, most modern dynamic routing protocols use either hop count or cost. Cost is another way to describe bandwidth. as common metrics, as common mechanisms to decide which path to take. And essentially a route with the best or smallest metric, the number closest to 1, will be the one that is actually installed and used by the device for routing to that particular network. And then administrative distance is used to determine between routing protocols. Like any good standard, there are more than one to choose from, and deciding which one to use is actually an important part of what a router needs to do. So administrative distance has a bunch of statically defined or pre-configured values. Now, a connected route is one that is directly connected to the device. Obviously, it's pretty trustworthy. If you can see the thing that you're trying to route to connected directly to you, there's a fair bet that that's the best way to get there. So by default, it has a trustworthiness of 0, and 0 is good. Lower numbers are better. Essentially, anything with it that is directly connected is always going to end up in the routing table. Then there's static routes, and we'll talk about static routes a little bit later. But essentially, a static route is one that you manually define, usually at the command line, to define how to get from A to B. And then there's what we call our dynamic routing protocols in turn. So EIGRP is a routing protocol that was created by Cisco. So it's a Cisco proprietary protocol. And it has 3 different representations. It has what's called a summary route, which is essentially a roll-up of all of the networks known to a given device. It has an internal representation, which is used within a network, and then an external representation, which is used between networks. So you might, for example, see the external representation if you work for a company that has acquired another company and both companies use EIGRP. But the reason that these, in EIGRP's case, the reason that those particular trustworthinesses are taken is because in Cisco's view, a summary route is the most trustworthy. It's also the least specific. It tends to be a fairly broad swathe of a network. So it tends to be a good backup route with metric and specificity being more important. And then internal routes are always going to be preferred in EIGRP over external routes. So if you know 2 paths to a remote network and one is known to you internally and one is known to you over, say, the internet, it generally makes sense to pick the one that goes internally. Not least because if it's going over the internet, you could well be paying for that. Then there's BGP, Border Gateway Protocol, which is the main routing protocol or route information protocol used by the internet. And it too comes in 2 different flavors. It comes in an external form, which is used by, well, the whole internet, and an internal form, which particularly carriers and service providers would use to share information within their own networks. Now, this one you'll see is reversed compared to EIGRP. Externally learned routes are more valuable than internally learned routes. And that's really because you would not normally use BGP internally unless you're a service provider with very specific requirements. You're more likely to use one of these other protocols that are here in the middle, particularly OSPF, Open Shortest Path First, and ISIS, Intermediate System to Intermediate System, both of which I'll talk about a little bit later on. And then there's this one called unknown. Now that's a catch-all. Any route that is unknown or comes from an unknown source is considered untrustworthy and is not installed in the table. And that's so essentially that number there, 255, gives the routing table that representation. In short, if we see a route with an administrative distance of 255, we know not to use it. So lowest metric and lowest administrative distance will always win, and essentially mean in that order, those routes get installed in the table. Everything else sort of sits to the side until there's a problem or a change. So with that, I might just pause 20 minutes in, and see if we've got any questions to answer before we move on.
We do. We've got 2, which I think is a very nice number to answer.
Yep, brilliant. Okay, so stub routing, great question. You obviously are at least passingly familiar with OSPF. So stub routing, I'll give a very brief description, but what I'd like to do, if you don't mind, Adil, is if you could put that question into the forum when it opens a bit later on, I would love to give you a much more detailed answer there. Long and the short of it is a stub route or a stub router is a specialized construct within OSPF that allows for a summarized network to be made available to a larger network, and for that summarized network to not be exposed to all of the details of a much larger network. So it's very, very useful if, for example, you've got a very large and complicated network. Let's say you run a large university with hundreds of smaller satellite type sites. You would typically use stub routing or stubby areas to address that. And in a stub router, you would typically use both statics and defaults. You would typically have a default route advertised into or out of the stub area, depending on what sort of stub area it is. And you might well use static or directly connected routes in there as well. And to address that, additional question around AD cost, administrative distance cost, essentially it's the differentiation between routing protocols. So different routing protocols are deemed more trustworthy than others. Now, those numbers are, broadly speaking, arbitrary. There's no real reason that OSPF is deemed more trustworthy than ISIS, other than the fact that that's the way it's always been done. And then Greg asks, how do you differentiate internal versus external BGP? So administrative distance is used from a differentiation perspective. And typically, as you'll see on that previous screen, I'll just roll back to it. External BG or internal BGP has a higher administrative distance. You can think of higher administrative distance as being harder to get to than, say, OSPF. So typically in a carrier type network, you might use OSPF and BGP because they do, in the sense of a carrier network, provide very different functions. You'd typically use internal BGP to carry, say, customer networks, whereas OSPF you might typically use to carry the core of the network itself. Now, that difference in trustworthiness essentially means that if a given route is known through both OSPF and through internal BGP, it's always going to be learned from OSPF, no matter what internal BGP says or does. Now, internal versus external BGP, we'll actually be talking a little bit about BGP a little bit later on, but essentially the way that routers determine which is to look at what's called an autonomous system number. And if the device that it's talking to has the same autonomous system number, then it's part of the same autonomous system, which is to say it's part of the same business or part of the same organization. If it has a different one, then it's a different organization. Therefore, it's external BGP, and the routing table will be reflected accordingly. And I will answer that question from Vincent very, very quickly. When a packet is addressed to an unknown destination, how does a router handle it? We'll actually discuss that in a little bit of depth, but essentially, if it's unknown, the router will discard the packet. It will send it to the great big bit bucket in the sky. And I'll move on now. Okay, so what does a router do? We've kind of covered off the theory of it, but here's a Cisco iOS command line. If you log into a Cisco router, type the enable command, you'll get a prompt that typically starts with a hash. That's the elevated prompt. You can then type the show IP route command, which will in turn give you output that looks not dissimilar to this. So what that output tells me is that we've learnt 2 routes, both directly connected. We've learnt the network 192.168.1.0, and it's connected physically to fast Ethernet 00, which happens to be the first Ethernet port on what is clearly probably a fairly old router these days, because fast Ethernet means 100 megabits per second or potentially slower. And then we know another directly connected route, 192.168.2.0/24, which is connected via a serial port. So this is almost certainly, based on this diagram, 192.168.1.0 on the left-hand side of R1 and 192.168.2.0 on the right-hand side of R1 connected to S2. That in summary is what you might see on a small router, say a consumer grade or maybe a Cisco 800 or similar relatively small device that you might have connected to your internet service provider. And in the case of your own personal ISP, you're almost certainly only going to use directly connected routes. You might statically define a default route so that the router knows to send all traffic that's destined for the internet out your serial port, or more commonly these days, out your WAN port. But that, in a sense, is exactly what this router is doing. Pretty straightforward at this point. There's nothing too special here going on here. We're just dealing with directly connected routes. So routers interconnect networks and form internetworks. So the internet is a internetwork. It is certainly not the only internetwork. And there's generally a one-to-one relationship between interfaces and subnets. So generally, and there are exceptions, you'll have a single Ethernet interface or maybe an SVI, a switched virtual interface that's tied to a VLAN, which is a sub-interface, another word for a sub-interface. But typically that'll have an IP address tied to it. It'll have exactly one IP address tied to it. They don't need to be physical ports. Obviously, if you've got, say, 15 VLANs and a router with only 4 ports, that's still a perfectly reasonable configuration, and that'll work fine as long as you're tying those IP addresses to those sub-interfaces. It is possible to have more than one IP address or more than one subnetwork on an interface. For the purposes of the exams, it's not something you would typically see, but it is possible to do, and there are good reasons why you might need to, particularly if, for example, you're working in a large, complicated environment where all of a sudden the need for more than a certain number of hosts on a given network has appeared. Let's say there's been a merger and you've suddenly got twice as many staff in an area than you had. You might, as a stopgap measure, just simply add more IP addresses to a given network, in which case you would likely just add another IP address, another network to that existing interface. It's not generally best practice if you can avoid it, but it is possible to do. And without getting into the detail, with IPv6, it's actually very common that IPv6 will do that to you automatically. IPv6 tends to be quite profligate in its use of IPs, partly because it can. Now, a big part of what a router does is choosing the best path to get from A to B. So if you look at, say, an internet router, say you somehow manage to gain login access to your internet service provider's core or a core device at your ISP, you'd very quickly see, if you did a show IP route 8.8.8.8, for example, you'd likely see potentially 15 or 20 ways to get there appearing in the routing table. Now, how does it choose which one to pick? Because obviously, you're not generally going to want to pick more than one of those. There's a few different ways it can do it. Obviously, you can install a route using a static route, and per administrative distance, that will tend to win. It can learn it because it's directly connected to the device. or it can learn it from one of the multitude of dynamic routing protocols. Or more commonly, it'll learn it from multiple sources, depending on the importance of the network or device that you're trying to connect to. Routing tables are basically used to make those determinations, and they'll use administrative distance, they'll use metric, and they'll use prefix length to make those determinations. Once they've done that, they will add new layer 2 headers and send it out the right interface to get it to the next path, the next part of the network. Bear in mind that particularly in, say, the internet's case, a router can't see anything beyond its immediate neighbors. So all it can really do is address the frame, the layer 2 components of the packet, to the next router in the path, and hope that that next router does the right thing by it once it gets that frame delivered to it. We'll talk about encapsulation and decapsulation fairly shortly as well. So how does it do that again? So realistically, what it does is it uses metric first and foremost, along with prefix length. So assuming that the prefix length is the same for two different networks, then metric is the next best measure that it has. And metric is typically cost. If there's a network with higher bandwidth, if you're using, say, OSPF, then that is going to be preferred. That path is going to be preferred over one with lower bandwidth. In the case of BGP, it will use information shared by the neighbors to determine what the best path is, such as the number of subsequent hops between that device and where the packet needs to go. Either way, the best path is the path with the lowest metric. And different protocols determine this in different ways. So there's an older protocol called RIP, Routing Information Protocol, which is pretty simple. It just uses hop count. What's the smallest number of routers I need to send this packet through to get from A to B? Then there's OSPF, Open Shortest Path First, which is essentially designed to prefer the fattest pipes, the widest bandwidth, the highest speed links between A and B. So if you've got a primary path that consists of, say, 400 gigabit Ethernet links and a backup path that's only 10 gigabit Ethernet links, then OSPF by design will always choose the faster link. Whereas depending on how your network looks, it's very possible that RIP might choose the slower path if, say, that path was more direct. Both have their advantages, both have their disadvantages, but these days you're more likely to see OSPF in a modern network than you are to see RIP. In terms of encapsulation and decapsulation, what a router essentially does, it doesn't touch any of the layer 4, 5, 6, and 7. It just reads layer 3 and works from that. But as it moves from PC1 through router 1 through router 2, essentially at each step, layers 1 and 2 get replaced with the MAC address and framing type for the next segment. Layer 3 doesn't need to be touched because it only consists of the destination information, in this case PC2, and then passes that on to the very next router. So essentially, router just takes in the packet, looks up layer 3, figures out where it needs to go, adds its own new layer 2, removing the old layer 2 information, and passes it on to its neighbor, who does the same until, oh, look, we're at the destination we wanted to get to. So essentially, the way that works is that R3 will end up punting this on to ultimately to PC2 by the time it gets to the end, having read the destination information the whole way through, and basically only knowing that this packet was delivered by its immediate neighbor on the left-hand side, in this case, R2. So it has no real knowledge of the whereabouts of PC1. And in this particular network, it doesn't really need to care either, other than the fact that it knows it can get back to PC1 by talking to R2. And then R2, sort of working backwards, R2 is taking the same approach, essentially just changing the layer 2 headers to pass that information on as it moves from A to B. Now, before I move on, have we got any questions?
Yes, we have a number of questions. I'm going to let you decide on which ones you would like to answer.
Cool. All right. So do we have versions in OSPF? Yes, we do. There's really only two that you're going to need to deal with. There's OSPF version 2, which these days is just called OSPF. And there's OSPF version 3, which is optimized for IP version 6. So IPv6 uses OSPF v3, and IPv4 tends to use OSPF or OSPF v2. Now, Philip's also asked, what's the difference between OSPF and MPLS? That's a huge question. I will give a very brief answer here, but Philip, if you'd like to put that question in the forum once it opens, I'm more than happy to give a much longer answer. Essentially, OSPF's a routing protocol. Open shortest path first. Its job is to tell routers how to get from A to B, whereas MPLS, multi-protocol label switching, is actually a mechanism that routers can use to distribute traffic through a network. So you can have OSPF and MPLS working together. It's not an uncommon situation, but they actually do provide very different functions. One's a routing protocol and one's designed to distribute traffic. MPLS can often be thought of as sort of layer 2.5 protocol. Relies on layer 3, but allows you to transport a lot more than that. And I'll answer one more. Shub asks, are there any effects to the cost calculation based on what port a routes are linked to? In the case of protocols like OSPF, yes, because a faster port will lead to a lower cost or lower metric, and therefore will be preferred over a slower port. So if you've got a 400 gig port and a 1 gig port on the same device, and both have valid routes and there is nothing else to split them, OSPF is going to choose the faster port every time. And I'll move on. Okay, so load balancing. When a router has 2 or more paths, let's say we've walked through the routing table and we now have 2 routes that are both learnt from, say, OSPF. They're both equidistant. Let's say they're both 1 hop away and they're both available via an equal sized link, say a 100 gigabit Ethernet path. In that case, what does the router do? Real simple. It will use both. It will install both routes in the table and it will use both links. So essentially what then happens is that you don't have 200 gig of throughput, you have 2 100 gig links, and that distinction is important. I'll explain why in just a moment. But essentially what it means is that both of those links will get used and both of those links will end up with a roughly equal amount of traffic on them. And that's called equal cost load balancing. You can do that with static routes as well. And it's actually a very, very powerful tool also to build availability into a network. Because if one of those 2 links goes away, the impact on existing traffic can be a lot lower than if you lost a single link. Obviously, some flows are going to be impacted, but hopefully not too many. Now, in terms of modern routing protocols, RIP and OSPF in the sense of an internal gateway protocol, in other words, something you'd use within a corporate network, for example, both support it, and it is possible to use it with other routing protocols as well. Now, it is important to note, though, that because of the way networks work, we don't see completely perfectly equal traffic distribution across those links. And we can't, because there can be all sorts of conditions on the network that might cause one packet to be delivered before another, in other words, out of sequence. And protocols like TCP do not like that. So what a router will do is it will pick a path for a given conversation, a given flow between two devices, and it will stick to that path for as long as that flow is in use. The return path might be the same, it might not be, but essentially to guarantee that, the first packet always arrives before the second packet in a given conversation between two devices, routers will always decide on the same path for that particular flow until such time as that flow is no longer in use. And typically they'll use various mathematical techniques like hashing to do so. So they'll pick all sorts of different mechanisms to make that happen and do so in basically a self-consistent way. Then we talk about the routing table. So obviously all of this needs to be stored somewhere. Now the current internet has, at last count, just shy of 1 million networks known to it, 1 million discrete networks, 1 million autonomous systems, if you will, or you can think of it as 1 million organizations that are directly connected to the internet and who are big enough to essentially have their own routing presence on the internet. Now, one of those million will be your internet service provider, for example. One of those million might be AWS, for example. One of those million is Charles Sturt University, for example. So we're talking reasonably large organizations here. But regardless of that, and that's important because obviously learning 1 million routes is a lot easier than learning, say, 9 billion or so, one route for every person, for example. And so we do use a lot of things like summarization to make this a lot easier. But 1 million routes, 1 million prefixes is still a lot of information to learn. So that needs to go somewhere. And obviously, from a computer's point of view, and for these purposes, a router can be considered to be a specialized computer. Memory, RAM, is the best place for that information. Now, obviously, that means that when the device reboots, it's got to learn it all again from scratch, and that poses its own challenges. But the long and the short of it is, it's a table, it's stored in memory, and that basically acts as the white pages, if you will, of how to access every possible device on the internet, using summarization if needed. So when I talk about summarization, think of it similar to the old telephone exchanges where to make a long distance call, you couldn't call a number directly. What you had to do was get put through to an operator who would finalize the call for you. That's essentially what's happening here when I talk about summarization. A router knows how to get to another point on the network and essentially asks for that other point on the network, a subsequent router, to finish the call, to get me to where I need to go. That routing table contains all of the routes known to the router, and it is known in routing and networking terms as the RIB, or the routing information base. The layer 2 equivalent, by the way, is called the FIB, the forwarding information base. So you will, in the exam, tend to see the two terms used. They both perform essentially the same functions. The RIB does so at layer 3 and tells a router how to route, and the FIB does so at layer 2 and tells a switch how to switch. Now, there's a really useful command to show that table, and this works on pretty much every router that exists, regardless of who makes it. Show IP route is that command. And that'll show you all of the routes that it knows. That can be to many, many, many thousands of pages if it's a big table. There is a command, you can pipe it through the more command to paginate that information. And you can also do show IP route and a particular address if you're interested in that, in how to get to that specific address. If you're troubleshooting a routing problem, you might do show IP route 8.8.8.8, for example. And that'll tell you what that router thinks is the best way to get to that address. And then you can compare that with your network design and figure out whether, whether the router has it right or whether it's learnt that information in error somehow. And then you troubleshoot from there. What does the routing table look like? Pretty straightforward. We did a show IP route before. Here's a different version. This one's learning a route dynamically. So this D in this left-hand column, and on the next page, I'll show you what all of this means. Basically means it's learning this route from EIGRP. So it's not been manually configured into this device and it's not a directly connected. It's being learnt from a dynamic routing protocol. And that's useful because that immediately tells us what administrative distance is being used to determine how to get to this particular network. And in turn, why this particular route has been chosen as the best possible path. So what does that look like in terms of the individual sections? So the D, this is just that last line from the previous slide. So the D is EIGRP in this case. Don't ask me why it's D and not E. That was Cisco's choice. Then the network itself, in this case, 10.1.1.0/24. So it's that network of 10.1.1.0, containing hosts from 10.1.1.1 through to 10.1.1.254. Then we've got the administrative distance, in this case, EIGRP with an administrative distance of 90. Then we've got the metric, and again, smaller is better. EIGRP has some funny ideas on what small looks like. But essentially, this route is the best possible path to this network. And then, how is that? How do we get to that device? In this case, we're connecting to a device 209.165.200.226, which happens to be at the other end of the serial link. And we've known this route for 5 seconds. So clearly, in this case, that serial link has just come up. Now, if that route, if in 10 seconds time, it's still only been learnt for 5 seconds, there's a possible troubleshooting problem. Maybe this link keeps flapping or being disconnected and reconnected, for example. IPv6, just for completeness, similar deal. Show IPv6 route is the command though, rather than show IP route. And similar deal, in this case, we have a directly connected route, which happens to be via Gigabit Ethernet 0. So the very first Gigabit Ethernet port on this device. And we're learning a route via, let me see if I can find, we're learning a local route, sorry, which is a specific IPv6 construct. Essentially, we have a route advertisement of this /128 from the local device. Now, /128 is a very specific address in IPv6. In other words, it is as specific as it gets, like a /32 is for IPv4. And it happens to be this particular device. In other words, we are learning our own routes into this table as well. And the main reason we might want to do that is so we can redistribute those routes. Redistribute means share them with other devices using one of these dynamic routing protocols here. ISIS, for example, or OSPF, or even BGP or RIP. Static routes. So statics are routes that you configure by hand. They're routes that you'd put into the configuration itself. Now, they're not scalable for obvious reasons. You don't want to be changing routes all day. That's where dynamic routing protocols really come into their own. But there might be specific routes that you want to always be known no matter what happens. That might be your default route, which is the default being the standard path to, say, the internet. So someone asked earlier about what happens when a packet can't be routed, can't go to, or the destination is not known and it gets dropped. That's the default behavior. But if you have a default route that says, in this case, IP route 0000 space 0000, what you're saying is, for anything you don't know, send it to this guy and let him figure it out. So you essentially define a static default route that says, send everything you don't recognize to your internet service provider, and if they don't figure it out, they'll discard it instead for you. So statics are really good for that sort of use case, and they might be useful if, for example, you really do need to control how your traffic is getting from A to B. Generally speaking, though, dynamic routing protocols are a far better way to manage the day-to-day. What does a static look like? So IP route 0000 out through serial 0. So essentially, we're just saying for this router, anything you don't recognize, just send to R2 and let it figure it out. And when you do a show IP route, it says gateway of last resort is essentially that serial link 000. And we know that to get to it, it's a static and it's directly connected via serial 0. So it's always going to go that way no matter what happens and no matter what anything else says to do, which is a good backup plan. But obviously, if you actually had to learn that route from a different path, that's not going to work for you. You're going to need to start thinking about, tweaking metrics and so on. Now, these other routes, they're more specific. So 192.168.10.0/24, for example, that's a more specific route than 0000. So it's still learnt and it'll still be used instead of 0000. Dynamic routing. So dynamic routing is used to, as I said, share that information between devices and really stop you having to manually configure every possible network. Think about what it would mean if you had to configure every single network that, say, Microsoft have, and they have quite a few, and define how you are going to get to them. Now, obviously, if you've only got a single internet link, as most of you do at home, that's pretty simple. Just use that static default 0000 network and all is well. But if you're the internet service provider, that's clearly not going to work because you've probably got 15 different ways to get there. You probably peer, as it's called in the industry, with other service providers, with other carriers, maybe even with Microsoft directly yourself. And in that case, you don't want to be manually typing in, hundreds of networks. It's just not scalable. So with that in mind, we have dynamic routing protocols to do the hard work for us. And essentially, it's a way for a router to advertise to its neighbors the networks that it knows about. So in this case, with EIGRP, the protocol in use, R1 tells R2 that, hey, I know these networks. R2 says, hey, yeah, cool, I know these networks as well, these different networks. And by the way, I also know how to get to the internet. So R1 then goes, great, I now know how to get to all of these devices because all I need to do is pass that traffic straight on to R2 and let it figure it out. And the reverse is also true. So in summary, that's what a dynamic routing protocol does for you. In terms of those protocols, we've touched on a few of them already, but IS-IS, intermediate system to intermediate system, is one that you would only really see in the service provider space. It is a very powerful routing protocol. You're not likely to see it. You certainly won't see it in the exams, and you're not likely to see it in a typical corporate. It does things in a very similar way to OSPF. The difference is that unlike OSPF, it is actually designed in a very industry neutral way. OSPF was built around IPv4, and that has some shortcomings and fallbacks as a result. But at the same time, it works, it scales well, and it is pretty much the de facto standard in most large organizations these days. Then there's RIP. RIP is a much older protocol, been around a very long time nowadays. And it has the biggest issue that because it only uses the number of hops to get to get from A to B as its metric, you end up with a situation, as I described before, where you can have it preferencing a link which is actually lower bandwidth and is really designed as a backup because it looks shorter, which is not a great outcome by anyone's measure. And then there's border gateway protocol. Now, BGP is included really for completeness. BGP is really only used on the internet and for the internet, again, unless you're a service provider. It's a very, very, very powerful protocol, but it's actually not, strictly speaking, a routing protocol. The thing that makes the first three a routing protocol is that they all advertise directly paths to get from A to B. And that information is trusted implicitly by the routers once they receive it. So if a router says, hey, I can get to this device and it's got a cost of Y to get there for me, the router down the chain says, yep, great, no worries, I trust that. BGP is really designed more for service providers, and therefore it actually allows the application of policy to that information. So essentially, because the internet's not a particularly trustworthy place, as most of you will be well aware, BGP allows people to make their own decisions on how trustworthy a particular path might be. Okay, IPv6 wise, we've got RIP next generation. We've got OSPF version 3. I mentioned that before. We've got ISIS. There is no change in ISIS between IPv4 and IPv6. That's how platform neutral it is. And then there's a special case for IPv6, which is a multicast version of BGP. Now, why do we care about all of this? Really kind of touched on this already, but just to recap, the biggest reason is it's a lot easier to discover how to get from A to B if you don't have to manually configure it each time. It means things get updated pretty quickly. You know, OSPF can make a new routing decision, you know, within a few milliseconds in a well-built network. So generally, if there is a failure somewhere on the network, it doesn't affect too much at layer 3. And as a result, you know, it's generally pretty good at picking the right way to get from A to B. And if something goes wrong, it's very, very quick at fixing that as well. If you were doing everything manually and there was a failure on the network, you'd actually have to log into probably 2 or 3 routers, maybe more, and manually reconfigure those. Not really very scalable. Right, any questions before we move on?
There's an abundance of questions if you would like. I'm going to limit you to 2 fairly
2
short answers just for time.
Yep. No worries. So anyone whose answers I don't get to, please feel free to put them in the forum, and I will do my level best to get to them before next week. Yeah, because there were a lot of great questions last week, and I didn't get to all of them. Is it possible to know how a packet will be routed from an end user's perspective? The short answer is not really, unfortunately. If you are on the internet, which clearly you are, you might want to look up what are called looking glasses. So if you do a Google search for looking glass, 2 words, you might find viewports into the routing of various internet connected hosts. So for example, there's a big internet service provider in the US called Hurricane Electric. They run a public looking glass, which allows you to see the internet from their perspective as opposed to your own. And so you can use that sort of information to derive how your packets might get routed. You can obviously do it empirically. You can use tools like traceroute, which will give you some, not information, not complete, but certainly some information on how to get from A to B. But yeah, so in short, though, unfortunately, no. Troubleshooting is something that really needs command line access to a router to do. And then Greg asks, can you have IP route 00 to multiple interfaces? Absolutely, yes, you can. That would just be a special case of equal cost multipath routing. So as a personal example, I do have 2 ISP connections here at home, and I do have 2 default routes on my Juniper SRX router that connects me to the internet. Okay, and since I'm limited to 2 questions, I'll keep moving on. All right, so basic components of routing. EIGRP is the example here when it comes to dynamic routing protocols. You will notice that I did not include EIGRP on the previous slides. And that's because while Cisco do still talk in terms of EIGRP, it's not actually commonly used anymore for the simple fact that it only works on Cisco devices. And of course, the internet is much bigger than Cisco. Even Cisco these days have tended to deprecate EIGRP. But essentially what a routing protocol does is it builds the routing table. It builds two parts to that, what's called a neighbor table. So what are the nearest routers to me? And a topology table. What does the whole network look like from the perspective of the routers? It uses a bunch of messages to do so, messages called hello messages, which allow the routers to establish communication, then updates and queries to confirm and validate that information, replies to that information, and acknowledgements, which essentially acknowledge a change in state. And then they also tend to negotiate with each other on the best way to share that information. So EIGRP is a good example in that sense. OSPF does work in broadly similar ways in a lot of respects. It is a different type of routing protocol, and we'll talk about that in a minute. But the long and the short of it is that there are, the basic concepts and structures you see here are broadly shared across the different internal routing protocols. So advantages, obviously, we've gone through those. A lot easier than doing it by hand. It's much more self-healing. If there's a problem on the network, protocols like OSPF can generally deal with it as long as the network architecture is well considered. And probably the only real disadvantages, and these days they're not huge problems, is they are computationally expensive, particularly in a large network. A large core router on the internet might take 5 to 10 minutes to boot and start actually routing because it takes that long for it to actually load up a million routes and figure out what to do with them. And you might want to answer this in the chat, but I'm sure you can think of some other examples of when static routing might be more appropriate. Obviously, a default route, particularly if you're connected to a single internet service provider, is probably all you need, and a static router is going to be a lot less overhead than say configuring OSPF, if indeed your service provider would even let you do that. But maybe you might want to put in the chat some other suggestions on when statics might be appropriate. So just to recap again, this is important. This is information that you will need for any of the 3 exams we've been talking about. Routers send and receive routing messages when it comes to a dynamic routing protocol. That's how they determine, what networks are accessible, how to get there. They'll share that information with each other, so they all basically form the same picture of what the network they're connected to looks like. And when there is a change on that network, let's say an interface goes down, or a backhoe gets involved and digs up a cable and breaks it. Once the routers realize that's happened, they'll tell their neighbors about it too, so that everybody's working to the same hymn sheet. Now, all this comes back to a concept called convergence. So convergence in an internal network, an internally routed network, that is to say your enterprise network, is considered converged when every router agrees on the best way to get from any given A to any given B on that network. So convergence time is how long does that take? Because obviously that's a pretty important consideration, because until all of the routers agree, there's a risk of traffic getting lost. Or to the question that was asked earlier about what happens when a network isn't known, or a router doesn't know how to get to a particular part of a network, it'll just discard that packet. It won't put any more thought into it than that. So if you've got a non-converged network, there's a risk of that occurring. And in turn, well, that's not great. It tends to cause issues. So Different networks, different routing protocols do this differently, and therefore take different amounts of time to do so. RIP, for example, is comparatively slow to do so because every router does its thing in turn, advertises to its neighbors. That might in turn cause a ripple effect through the rest of the network. So it can, in some cases, in large networks, take quite a long time for RIP to decide how to, what the network actually looks like. Whereas OSPF actually elects two designated routers, a primary and a backup, that essentially act as the orchestrators for the whole network. So once the network topology is known, and there's what's called a link state database that OSPF maintains, that's shared from that core device out to every other device on the network. So there can be no disagreement between devices about what the network looks like, and therefore convergence is generally pretty quick. And similarly, if there's a change to the network, say a link fails or somebody plugs something new in, likewise, OSPF is generally pretty quick, even on a very large network, to figure that out, because there's really only one device that has to make that decision and then distribute that information to all of the other devices. Now, there are multiple ways to figure out what a network looks like, bearing in mind that a router can only see its immediate neighbors. And essentially, they come down to broadly two different types of routing protocol. So there are what are called the distance vector routing protocols, which essentially just work on hop count. That is to say, they count the number of routers that need to be talked to in order to get a packet from A to B, and smaller numbers of hops is better. And then there's what are called the link state routing protocols, which take into account the total bandwidth available between 2 points on the network. So essentially, they build up a total picture of the whole network, and they will trade off, say, a 2-hop path, which might have 400 gigabit Ethernet links, versus a 1-hop path that has, say, a 10 gigabit link. And they're going to pick the 400 gig path every time, given the choice, even though there's an extra hop involved. And that makes sense because obviously, chances are the 10 gig link has been, nailed up as a backup, and you don't want traffic on that unless something's gone very wrong. You want to use your 400 gig links. You've probably paid a lot for them. So these days in a common modern network, you'll typically see link state routing protocols used, and typically OSPF or OSPF v3, or usually both if you're running IPv6. You'll see OSPF and you'll see OSPF v3 for the IPv6 network. And then off to one side, the only real external gateway protocol that you'll see these days is BGP. That's because the whole internet uses it. And the whole internet kind of has to agree to use it, because if we all tried to use different routing protocols, the internet wouldn't work. And it actually uses what's called path vectoring. So it actually looks at the number of autonomous systems, the number of service providers and other networks that it has to go through, as well as a bunch of other information, including, as I indicated earlier, a bunch of information about policy. So in BGP, you can define that a particular path is your preferred, and you might want to do that for, say, commercial reasons. It might be cheaper to send traffic a particular way. IGPs versus EGPs. Interior are used within what is called, in networking terms, an autonomous system. Now, an autonomous system, as I said before, is broadly speaking an enterprise or an internet service provider, or it's a logical, self-contained unit of a network. It's usually multiple networks, of course, but it's usually something that's, administratively a single component. And typically in these, you'd see RIP, EIGRP maybe, OSPF almost certainly, and possibly IS. And then BGP for everything else, for the external gateway protocols. So that's used between service providers, between cloud providers, between large businesses. Distance vector versus link state. Touched on this a little bit before, but essentially distance vectors just use the number of hops. So how many hops are there between point A and point B? And I've actually got a couple of diagrams that describe that on the next couple of slides. So link state, it's pretty much the opposite. Rather than just knowing the number of hops to get from A to B, a link state routing protocol actually looks at the whole network holistically and figures out which links have the most bandwidth and uses them accordingly. And there's a little bit of CompTIA coming up too, just as a warning, a little bit of computer science to be talked about here. So distance vector, really, it's just the number of hops. You know, one hop is better than two from its perspective, which is better than three, all the way out to usually a maximum of about 8 hops, which also gives you an absolute upper limit on the size of a RIP network. It really can't be that big. So RIP v2 is probably the most common one you would see if you do see RIP. It's been around a long time. And IGRP and EIGRP are pretty rarely used these days, unless it's a purely Cisco network, which, of course, these days is a reasonably uncommon thing. Then there's the link state ones. There's a link state database involved that's managed and orchestrated from a single router called the DR, the designated router. And it has a backup called the backup designated router, whose job is to step in if the designated router can no longer drive. And essentially, they just use the amount of bandwidth that's available on any given link to make a forwarding decision. We touched on metric before. Metric is cost. It's how expensive is it to get from A to B? And just like expense when you're talking about your personal budget, smaller numbers are better. The less money you're spending, the less something costs, the better it is. So a lower metric, a lower cost is always going to be preferred. And so routing protocols will use various mechanisms to determine what that cost should be. And again, using OSPF as the example, it's going to use things like the amount of aggregated bandwidth available between 2 points on the network. Quick touch on OSPF version 3. It's like OSPF v2, or just plain OSPF, if you will. It's built around a link state concept. Pretty much every vendor now supports it very well indeed. So there's generally no meaningful interoperability challenges. Cisco to Juniper, HP to Cisco to Juniper, Extreme Networks, all of these vendors, VMware, they all support it very well indeed. It only supports IPv4 and IPv6. Now, in 99 out of 100 cases, that's all you need, so that's fine. It uses cost as metric, which is bandwidth, and it uses Dijkstra to determine the best path. And that's the CompTIA bit that we'll get to on the next slide. So OSPF and OSPF v3 are the most common protocols you'd see in a large network. And certainly the exams reflect that. So Dijkstra's algorithm essentially just adds up the costs on each link, with cost being an inverse number based on the link capacity. So essentially, the faster the link, the smaller the cost. So a 400 gig link might have a cost of 2, a 1 gig link might have a cost of 20. So it basically totes up the costs for any given path on that network, and that cost is then your shortest path. So if there's 4 different ways to get from the top of R2 to the middle of R3, it's going to pick the one that ends up being the smallest aggregate number once all of those different paths have been calculated. So that calculation can be quite slow, which is why it's only ever done by one device, and then that information is then propagated out to everybody. So what does this look like in the case of routing protocol? So again, we've got a static route here. We're learning routes from a bunch of different dynamic routing protocols. And you'll see there's a bunch of different costs associated with that as well. What do these look like? We've got a route source, obviously. what, basically how is that route learnt? What's the network? What's the cost of that? Or what's that's actually incorrect. That's not administrative distance. That's prefix length. Bigger numbers are better. Then you've got administrative distance here and metric. You've got the next hop, i.e. how are we getting to this network? Being that we don't necessarily know exactly where this exists. We just know that the best way is to ask this guy. How long has it been known for, and how are we getting there? Any questions before I move on?
Quite a few. I'm going to limit you to one question before
One question?
before the final Q&A session at the end.
No problem at all. Okay. Okay, so Stephen's asked a really good question about, based on discussion last week to avoid loops, if there's a break in a link, will this require reconvergence? And after the broken link is restored, another reconvergence? In short, yes. So any changes to the network topology will cause reconvergence to occur. Now, for a protocol like OSPF, that's pretty straightforward because what OSPF will do is simply, if the link goes away, remove any paths that use that link. And when the link gets reestablished, it will simply recalculate those paths again. Maybe it's been broken because you're upgrading it from, say, 10 gig to 100 gig, in which case, once it reconverges, it's going to recalculate those and determine potentially that it's actually a shorter path for some, or a better path for some networks than for others. And for anyone else, please feel free to throw the questions into the forum. And again, I will do my level best to answer as many as I can over the next week. So best route is always the longest possible match. So if we look at at an IP address in its binary form, the network is generally the first 3 octets of this construct. In this case, it's actually a little bit more. But either way, essentially the most significant component of it from a networking perspective is the first part of the address. Now, in this case, we know this particular host, 172.16.0.10, by 3 different routes. We know it by 00/12, we know it by 00/18, and we know it by 00/26, which happens to be this construct here. /26 is more specific than a /24. /24 would end at that full stop there in binary notation. Now, the more specific address is the one we're going to use. These other two might still get you there, but they possibly get you there by a more circuitous route, potentially through another router, potentially through what's called an aggregate address. Constructs like that might be why you would see 3 different paths to a given host. Either way, routers will always, given the choice, pick the longest possible match to determine how to get the traffic to where it needs to go. IPv6, very, very similar. Now, in the first week, we talked a little bit about IPv4 class structures, class A, B, and C. IPv6 has nothing of the sort. So it's all equivalent to what in IPv4 is now called CIDR. Unfortunately, that's not the drink. That's the concept of classless interdomain routing. So IPv6 is all classless. There's no differentiation between class A, B, and C in IPv6. So IPv4, though, IPv6, other than the size of the addresses, they're 4 times bigger, 128 bits instead of 32, are very much the same. So IPv6, show IPv6 route broadly looks the same as an show IP route command. You've got where does the route come from? You've got the network that you're connecting to. In this case, it's a /64, which is a common size for a local area network or a VLAN. We've got the administrative distance. In this case, it's learnt via EIGRP, so it has an administrative distance of 90. We've got that ridiculously large, but also ridiculously small metric there again. And we're learning it from a specialized IPv6 address, something called a link local address, which is in turn says that this device is capable of using what is called route advertisement. But either way, this address is connected at the other end of this serial link. So in the case of that previous diagram of R1 to R2, they're clearly also running IPv6, and they're clearly capable of sharing information over EIGRP. Now, IP and IPv6 are different protocols. The only thing that they share is the letters I and P. So it is perfectly reasonable to have two different paths for IPv4 and IPv6 that ultimately get to the same destination. That's perfectly possible, perfectly reasonable in some cases, and almost expected. Don't make the mistake in troubleshooting that just because IPv4 is working the way you think it should, that IPv6 will automatically do the same. They are different. They need to be treated accordingly. Now we get into what happens with a multi-layer switch. So obviously last week we talked a lot about switching. We've touched on the fact that there are these constructs called multi-layer switches, which essentially are routers with lots and lots and lots of ports. And in most cases, your medium to high-end enterprise type switches will actually be perfectly capable of routing. And there might be perfectly good reasons to do that. So what you see here, this diagram here, is what in the industry would be called a router on a stick. So you have a switch, it's just doing switching. It's got VLAN 10 and VLAN 30 on it. And you have a router here that's got, in this case, 2 ports. It might just have 1 port with a trunk on it. And it's routing VLAN 10 and 30. So it's separating the broadcast domains of VLAN 10 and VLAN 30 from each other, with that switch just doing the job of switching. Now, wouldn't it be nice if you could not have to buy a router to do that? Turns out you can. You can get rid of that router, and you can have a multi-layer switch which terminates those VLANs onto switched virtual interfaces, SVIs, or sub-interfaces, and essentially allows those two separate broadcast domains to route between each other as if there was a router on a stick, like there is in this construct here. So in the past, you used a router. You typically would use separate physical interfaces. Maybe you'd use a trunk port. Either way, packets would go to the router. It would do its routing thing and send the traffic back to the switch, and then the switch would have to do its thing. And you were basically buying a lot of hardware from Cisco and spending a lot of money to do so. And really, these days, switches are pretty powerful things. Why would you want to do that? So router on a stick, that's essentially what that is. But it collapses it down where the previous diagram had 2 lines, 2 physical connections. You have one with sub-interfaces or SVIs to provide that config. And then obviously those hosts just use that sub-interface address, might be 192.168.1.1, for example, as their gateway address. Now, obviously, if we collapse that down, we throw away the router. We basically tell the switch it's now responsible for doing that. And we basically just take that same routing config and copy it onto the switch. What we do is we basically say, okay, VLAN 10 and VLAN 30 now have sub-interfaces assigned to them. VLAN 10s is called, well, VLAN 10, and VLAN 30s you'd probably call VLAN 30. You give them addresses, and then the device knows that those two networks are connected to each other. They're directly connected, that is, and therefore routing will happen with no further configuration required. Now, every vendor that I'm aware of defines a VLAN 1 virtual interface for you. And in fact, generally that's how you manage the device when you first switch it on. But you can essentially create as many of those as you like, up to the limit of the number of VLANs that the device will support. Some smaller devices might limit you to, say, a few hundred, but in practical terms, you can have as many of those virtual interfaces as you have VLANs. So it knows how to route. It'll typically talk routing protocols. To all intents and purposes, it is a router and it will work like a router. It just happens to have 48 ports instead of 8, for example. So, any questions?
Numerous questions. Take your pick, Anne.
Okay, brilliant. So we've got a few minutes left, not a huge amount, but let's go through, see what we can do. What's the border between static and dynamic routes when it comes to network size? My view is, realistically, if you've got more than, say, one internet connection, if you're a business that is, say, using, say, 2 ISPs for redundancy purposes or what have you, you're probably going to want to investigate some sort of dynamic routing, because you're probably going to, at some point, need to make a potentially financial decision about the best way to get traffic from A to B. Maybe one's cheaper for some traffic than others. Maybe some traffic's on net. Maybe you're in a free zone for some traffic on one service provider and not on another. So that's typically where you'd start looking at using dynamic routing. Difference between load balancing and failover? That's an excellent question. So the difference between load balancing and failover is, well, essentially nothing. If you've got load balancing, you also have failover in a routed sense. So if a link fails, all of the traffic that was on that link will be handled by the remaining available links. And indeed, in the case of things like OSPF, that extends to if a link fails, and there's a more expensive option that up until now wasn't used, it'll automatically start getting used straight away and generally very, very quickly. So generally, you can treat load balancing and failover as two sides of the same coin. And indeed, if you're getting one, you're getting the other if you do it right. If load balancing is used, how does the network guarantee packets arrive in the correct sequence? Great question. Main way it does it is to ensure that every packet associated with a given conversation between two devices uses the same path. So it uses tools like hashing algorithms to determine that, and essentially ensures that for that given conversation, a given link is always in use until that link is no longer available. And which is more common in enterprise, OSPF or EIGRP? These days, it's absolutely OSPF. I've only seen EIGRP in one network in my 25-year career, whereas I've seen OSPF and ISIS in probably hundreds, actually. And is it possible to have both RIP and OSPF? Absolutely, yes. You can have multiple routing protocols, and there are many good reasons why you might. You might have a small older device that only speaks RIP, so you might use RIP to speak to it and then redistribute from RIP into OSPF and vice versa, to save yourself the hassle of having to manage static default or default routes. I think probably best to answer the rest through the forums if people
I
want to
was
put them there.
about to say
Yeah, because we're
something
pretty
very
much out of
similar.
time. Unfortunately.
Fantastic. Well, not fantastic that we're out of time, but fantastic job. And thanks everyone to your questions as well. As Ian just said, any questions that weren't able to be answered, feel free, and in fact, feel encouraged to pop those into the student portal forums, which you can access along with the recordings from tonight, which should be uploaded within about 24 hours. The slides, reading materials, quizzes, etc., via learn.itmasters.edu.au. Also, very much encourage everybody once again to fill out the survey, which can also be found at that student portal location. If you're feeling inspired by this course and you'd like to jump in and study a full-length qualification with ITM and CSU, please direct yourself to eligibility on the IT Masters website. Fill out our eligibility form and we can tell you what your eligibility is for studying with us in a full-length grad certificate or master's degree. and also if you're eligible for any course credit, which can shorten your degree and keep your costs down as well. Thank you very much once again, Ian, for this fantastic content. And thanks, Kit, on the back end. This seems to have run very, very smoothly. Thanks once again to all of our wonderful participants. As I said, this recording will be uploaded within the next 24 hours and available via the student portal or on YouTube. That should be just about it from us. We'll see you here again for the final week of this course. Same time, same place next week. That will be 7:30 p.m. Australian Eastern Daylight Savings Time, or your local equivalent. I'll let everybody who put in the chat at the start of the session that they were coming to us from locations where it is very late at night or very early in the morning, depending on your perspective, get to bed now. And thanks again. See you all next week. Goodbye, good night, good morning, good evening, good afternoon, etc. Everybody, have a great time. Bye.